A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You ever have that feeling, Herman, where you wake up, grab your coffee, open your email, and you see that little notification from the RXiv daily feed? It is like a physical weight hitting your chest. You see 142 new papers in the computer science and machine learning category, and you just know that at least 5 of them are probably claiming to change the world forever. It is March 11th, 2026, and I feel like I am drowning in PDFs.
Oh, I know that feeling intimately, Corn. It is the modern researcher's version of the Sisyphus myth. You spend all day reading 3 papers, and while you were reading those 3, another 12 were uploaded. It is a relentless fire hose. And honestly, it is getting harder and harder to separate the signal from the noise, especially with the sheer volume we are seeing here in early 2026. We are looking at a world where over 150,000 AI-related papers are hitting arXiv every single year. That is not just a growth curve, it is a vertical wall.
And that is why I am so glad our housemate Daniel sent over this prompt today. He was asking about the papers that actually built the foundation we are standing on. Everyone talks about the 2017 Attention is All You Need paper, like it was the only thing that happened. It has become this singular mythic event, the Big Bang of the generative AI era. But there is a whole ecosystem of research that made that possible, and a whole world of research that has happened since. Beyond the history, Daniel wants to know how we actually survived the current deluge without losing our minds.
Herman Poppleberry here, and I am ready to dive into the archives. It is a great question because the Attention paper, the one that introduced the transformer, is definitely the celebrity of the group. But a celebrity needs a supporting cast, a director, and a crew to actually make a movie. In the AI world, there are papers that solve the stability problems, the efficiency problems, and the training problems that the transformer would have tripped over if they hadn't been solved first. If you only look at the transformer, you are looking at the steering wheel and ignoring the engine, the fuel, and the road itself.
Right, and we also need to talk about what is happening right now. We are no longer in that golden age of 2023 where you could reasonably keep up with the major breakthroughs by following a few people on social media. It is a full-blown data engineering challenge, just to filter your reading list. So today, we're going to look back at the giants whose shoulders we are standing on, look forward at the most interesting stuff from the last few months, and then give you a tactical guide on how to actually manage your information hygiene. We have touched on the history of AI before, specifically in episode 599, where we looked at the decades of innovation before ChatGPT. But today is about the specific documents, the actual papers, that changed the trajectory of the field.
I love that term, information hygiene. Because if you don't have it, your brain just becomes a cluttered mess of half-understood abstracts. You end up with what I call paper fatigue, where you know the names of every new model, but you don't actually understand how any of them work. It is a dangerous place for an engineer or a researcher to be.
So let's start with the history. If we look back before 2017, before the transformer changed everything, what is the one paper you think people overlook the most when they talk about the current generative AI boom?
For me, it has to be deep residual learning for image recognition by Kyming. He and his team at Microsoft Research back in late 2015. Most people know it as the ResNet paper. Even though it was originally about computer vision, the fundamental breakthrough, the residual connection, is literally the reason we can train deep networks today. Before ResNet, if you tried to make a neural network too deep, the gradients would just vanish or explode. The signal would get lost as it passed through the layers during the training process.
I remember that. It was like trying to play a game of telephone with 1,000 people. By the time the message got to the end, it was just static. You couldn't actually pass the learning back through the layers effectively.
And what Kyming he and his team realized was that instead of forcing every layer to learn a completely new representation, you could just let the layer learn the difference, the residual between the input and the output. You basically add a shortcut, a little highway where the original signal can bypass the layer and be added back in later. This simple architectural tweak allowed us to go from networks with 20 or 30 layers to networks with over 1,000 layers. If you look at the architecture of GPT-4 or any of the modern LLMs we are using in 2026, those residual connections are everywhere. They are the structural steel of the building.
And without those residual connections, the transformer wouldn't even work, right? Every modern model uses residual connections around every single sublayer. It is the only way to keep the training stable when you have billions or trillions of parameters.
Every single one. If the transformer is the beautiful glass facade, ResNet is the steel frame holding the whole thing up. And while we are on the topic of unsung heroes, we have to mention the papers on optimization and normalization. Things like Atom, a method for stochastic optimization by Kingma and Ba from 2014, or the original batch normalization paper. These aren't flashy, they don't generate cool images or write poetry, but they are the reason the models actually converge during training instead of just vibrating into chaos. If you use the wrong optimizer, your model never learns. It is like having a car with a massive engine but no transmission.
It is funny how we focus on the architecture that produces the output, but the math that makes the training stable is often where the real genius lies. It is like focusing on the steering wheel of a car but ignoring the fuel injection system. But what about the bridge between the raw models and the assistants we use today? Because the original transformer didn't know how to be a chatbot.
That is a crucial point. The paper that changed that was training language models to follow instructions with human feedback, often called the Instruct GPT paper from early 2022. This introduced the world to RLHF reinforcement learning from human feedback. Before this, LLMs were just really good at autocomplete. If you ask them a question, they might just give you more questions. RLHF was the process of aligning the model, so it actually understood the intent of a human prompt. That paper is the reason ChatGPT became a cultural phenomenon while previous models stayed in the lab.
So we have the structure from ResNet, the attention mechanism from the transformer, the optimization from Atom, and the alignment from the RLHF papers. That is the recipe for the modern AI world. But let's talk about efficiency, because that is where the real battle is being fought right now in 2026.
Right, we have to talk about FlashAttention, the original paper by Tri-Dow and his collaborators in 2022, and then the subsequent iterations. This is a great example of a paper that didn't change what the model does, but changed how it talks to the hardware. This is where it gets technical, but also really important for the economics of AI.
Explain why FlashAttention was such a game changer for the people actually paying the electricity bills. I know it has something to do with how the GPU actually handles memory.
So, the standard attention mechanism is mathematically elegant but computationally expensive. It scales quadratically with the sequence length. If you double the length of the text you are processing, the work the computer has to do quadruples. But the real bottleneck isn't just the math, it is the memory. Moving data between the fast memory on the GPU chip, the SRAM, and the slower main memory, the HBM, is very slow compared to the actual calculation. It is the memory wall.
So the processor is basically sitting around waiting for the data to arrive, like a high-speed chef waiting for a slow delivery truck.
Precisely. It is like having a world-class chef who has to walk to a grocery store 3 blocks away every time he needs a single onion. FlashAttention reorganized the calculation so the GPU could do more work with fewer trips to the main memory. It used a technique called tiling to keep the data on the fast chip as much as possible. When FlashAttention 3 came out in late 2025, it showed a 2x speedup on H100 clusters. That is huge. That is the difference between a model taking 3 months to train and taking 6 weeks. It effectively doubled the world's compute capacity for training transformers without building a single new factory.
That is incredible. And it shows why keeping an eye on these systems level papers is so vital. If you only read the high-level architectural papers, you miss the breakthroughs that actually make the technology viable at scale. It is the difference between a laboratory experiment and a global utility.
And it is not just about speed. It is about what those speeds enable. Because we can process longer sequences more efficiently, we are seeing the rise of these massive context windows. We are talking about models that can ingest entire libraries of code or hours of video in a single pass. That wouldn't be possible without the optimization work done in papers like FlashAttention or the more recent work on state space models or SSMs.
Let's talk about those SSMs for a second. We saw a huge shift toward things like Mamba and Jamba in late 2025. Why are people looking at alternatives to the transformer architecture now?
Because as great as the transformer is, that quadratic scaling I mentioned is still a problem for really long sequences, like trying to process a whole movie or a massive codebase. State space models offer linear scaling. In late 2025, the Mamba 2 paper showed that you could get transformer-level performance with much better efficiency at long lengths. It is a fundamental rethink of how a model remembers what it has seen. Instead of looking back at every single previous token, it maintains a compressed state of the world.
Which leads us perfectly into the very recent stuff. Daniel's prompt mentioned looking at late 2025 and early 2026. What has been crossing your desk lately that feels like it might be the next big pillar?
There is a paper that came out in January of this year, 2026, called Omni-World: Generative Dynamics in Latent Space. It is coming out of a consortium of researchers, and it is fascinating because it signals a shift away from just predicting the next token in a text string. Instead, it is about building what they call a world model.
We've talked about world models before, but usually in the context of robotics or self-driving cars. How is this different?
The Omni-World paper proposes a way for a model to maintain a consistent three-dimensional representation of a physical environment entirely within its hidden layers, its latent space. Instead of just generating a video or an image, the model is actually simulating the physics of the scene. If it generates a video of a glass falling off a table, it isn't just guessing what pixels look like based on patterns, it is calculating the trajectory and the impact. This allows for much higher consistency over long periods. It solves that weird hallucination problem where objects in AI videos just morph into other things or disappear when they go behind a tree.
That feels like a massive leap toward true agentic behavior. If a model actually understands the physical constraints of a world, it can plan and reason much more effectively than something that is just playing a very advanced version of autocomplete. It is moving from, what does a video of a cat look like, to how does a cat actually move through space?
And it ties back to another paper I've been obsessed with from late last year, which explored sub-agent delegation. We touched on this in episode 795, but the newer research is taking it to a level where the main model acts like a CEO, and it spawns these tiny, specialized submodels to handle specific tasks like formal verification of code or searching a specific database. The efficiency gains are wild because you aren't using a trillion parameter model to do a 10 billion parameter task. It is about modularity and specialization.
It is like the AI is developing its own internal corporate structure, which leads us to the second part of Daniel's question, and honestly, the part that I think our listeners are going to find most practical. How do we keep up? If there are 150,000 papers a year, even if you are a genius like you, Herman, you can't read them all. What is your actual workflow for navigating the arXiv firehose?
It starts with accepting that you will miss things. The FOMO, the fear of missing out, is the enemy of deep understanding. If you try to see everything, you see nothing. My strategy is built on a hierarchy of filters. I don't go to arXiv and just browse the new arrivals. That is a recipe for a headache and a very unproductive morning.
Right, because the titles are often misleading. Everyone wants to sound like they've solved AGI in their title to get those clicks and citations.
My first filter is actually human. I follow a very curated list of researchers on specialized platforms. But even better are the automated curation tools. There is a tool called Connected Papers that I use religiously. If I find one paper that is actually good, I plug it into Connected Papers, and it builds a visual graph of all the related research based on citation overlap. It shows you the hubs, the papers that everyone else is citing. If a paper is in the center of a massive web of citations, it is probably foundational. If it is an island out on the edge, it might be interesting, but it is less likely to be a core breakthrough.
That is a great tip. It is like looking for the intersections in a city. The busiest intersections are usually where the most important stuff is happening. What about newsletters? Do you still find value in the daily digests?
I do, but I've moved away from the generic ones. I really like AK's Daily Digest on social media. He has an incredible eye for what is trending in the developer community. But for deeper dives, I look at things like the batch from deep learning, AI. They do a great job of explaining why a paper matters, not just what it says. They provide the so what factor. But honestly, Corn, the biggest change in my workflow over the last year has been using the models themselves to help me read.
I was going to ask about that. Are you actually having an AI summarize the papers for you? Because I found that can be a bit of a double-edged sword. Sometimes the summary misses the subtle nuances that actually make the paper important, or it hallucinates a result that isn't actually in the data.
You are absolutely right. If you just ask for a summary, you get a generic blurb. My approach is what I call the code first verification strategy. When a new paper comes out that claims a big performance boost, I don't read the abstract first. I look for the GitHub link. In 2026, if you aren't providing a reproducible implementation, your paper is basically just a blog post with math symbols. I've become very cynical about paper-only releases.
That is a harsh but very necessary rule. It separates the theorists from the engineers. If you can't run it, it doesn't exist.
It really does. If there is code, I'll take the main training script or the model architecture file and feed that into a long context model. I'll ask it specific, probing questions. I don't say summarize this. I say, look at the attention implementation in this file. How does it handle the memory bottleneck compared to standard FlashAttention? Or identify the specific hyperparameters they are using for the optimizer. By looking at the code, I get the ground truth. The paper is the marketing. The code is the product.
That is such a crucial distinction. I think a lot of enthusiasts get caught up in the hype of the abstract. The abstract is designed to get the paper accepted to a conference like NeurIPS or ICML. The code is what actually has to run on a GPU. It is the difference between a brochure for a house and the actual blueprints.
And then there is the figure 2 rule. Almost every major AI paper has a diagram, usually on the second or third page, that shows the overall architecture. If I can't understand the core idea by looking at figure 2 and reading the caption, the authors probably haven't simplified the concept enough. The best papers, the ones like ResNet or the Transformer, have diagrams that are so clear they become iconic. You should be able to sketch the core idea on a napkin. If the diagram looks like a bowl of spaghetti, the idea probably isn't ready for prime time.
I love that. The napkin test. If you can't draw it, you don't understand it, and maybe they didn't either. But what about the different types of readers? Daniel asked how researchers, engineers, and enthusiasts approach this differently. I imagine your approach as an expert is very different from someone who just wants to know how this affects their job as a software developer.
Definitely. A researcher is looking for the gap. They are reading a paper thinking, what did they miss? What is the next logical step that I can write my own paper about? They are looking for the failure modes. They want to see the limitations section, which, by the way, is the most important part of any paper for a serious reader.
Most people skip the limitations section. They want to see the charts where the lines go up and to the right. They want to see the benchmarks where the new model beats GPT-4.
Which is a huge mistake. The limitations section is where the truth lives. It tells you where the model breaks. If a paper doesn't have a robust limitation section, I don't trust the results. Now, an engineer, on the other hand, doesn't care about the gap. They care about the implementation complexity. They are looking at a paper thinking, can I fit this into my existing pipeline? How much VRAM does this use? Does this require a custom CUDA kernel that is going to be a nightmare to maintain in production?
Right. They are looking for the practical trade-offs. If a paper says it is 10% more accurate, but it is 5 times slower, or requires a whole new hardware stack, an engineer is going to ignore it. They are looking for the drop-in improvements.
And then you have the enthusiasts, the curious people who listen to our show. For them, the goal shouldn't be to understand the calculus or the CUDA kernels. It should be to understand the second-order effects. If this paper on world models is correct, what does that mean for the future of video games? What does it mean for the future of remote work or digital twins? They should be looking for the aha moments where a new capability is unlocked. They are the ones who connect the dots between the lab and the real world.
So, for the enthusiast, it is more about the narrative of progress. How do these individual bricks build the wall? It is about the wah, rather than the how.
Precisely. And for everyone, I think the most important piece of advice I can give is the 80-20 rule. 80% of the actual progress in the field comes from about 20% of the papers. Your job isn't to read the 80% of filler, it is to find the 20% of hubs. And you do that by looking at what the experts are actually arguing about. If you see a heated debate on a research forum about a specific implementation detail, pay attention. That is where the friction is, and friction usually means something important is being moved.
I think there is also a danger of what I call research FOMO, where people feel like they aren't in the know if they haven't read the latest paper that was tweeted about 5 minutes ago. But the reality is that most of those breakthroughs are forgotten in 3 months. They are just noise in the system.
Oh, absolutely. I call it the RXiv hype cycle. A paper gets posted, it gets 1,000 retweets, everyone says it's the end of the transformer era, and then 3 weeks later someone realizes the benchmarks were flawed or the results weren't reproducible. If a paper is still being talked about 6 months after it was posted, that is when I really sit down and study it. Time is the best filter we have. If it has staying power, it has substance.
That is a very conservative approach to information, which I appreciate. Let the noise settle before you try to find the music. It saves a lot of mental energy.
It is the only way to stay sane, Corn. Especially in a place like Jerusalem, where we have enough going on without worrying about every single gradient descent variant that someone in a lab halfway across the world dreamed up at 3 in the morning. We need to focus on the signals that actually matter.
Fair point. So let's get tactical for a second. If someone is listening to this and they want to start building their own information hygiene stack today, what are the 3 tools or habits they should adopt?
Number 1, install a tool like Connected Papers or Research Rabbit. Use them to map out the citations of a paper you already like. It will visually show you the ecosystem. It turns a flat list of papers into a landscape you can navigate. It helps you see the ancestors and the descendants of an idea.
Okay, that is a great one. Visualizing the connections makes it much less overwhelming. What is number 2?
Number 2, create a filter, don't consume workflow. Pick 2 or 3 high-quality sources, maybe 1 newsletter like The Batch, 1 expert social media feed, and 1 developer forum like Hacker News or a specific Discord. If a paper doesn't show up in at least 2 of those places, don't read it yet. Let the community do the first pass of filtering for you. You don't have to be the scout, you can be the settler who comes in once the path is cleared.
I like that. Don't be the first person through the jungle. Let someone else clear the vines and deal with the snakes. And number 3?
Number 3 is the most important for actually learning, the PyTorch rule. If you find a paper that you think is truly revolutionary, try to implement the core mechanism in 50 lines of code or less. You don't need to train the whole model. Just try to write the math for the new attention head or the new normalization layer. The moment you try to code it, you realize where your understanding is fuzzy. It forces you to move from passive consumption to active creation. It turns the abstract into the concrete.
That is such a high bar, but I can see why it works. It is the difference between watching a cooking show and actually trying to bake the bread. You don't know if you understand the recipe until you are covered in flour and the oven is on.
And look, if you aren't a coder, the equivalent is to try and explain the paper to a friend or a brother in plain English without using any buzzwords. If you have to use the word stochastic or multi-head or latent dynamics to explain it, you might not actually get the core concept yet. True understanding is the ability to simplify.
That is a challenge I take to heart every time we do this show. Speaking of which, we should probably start wrapping this up. We've covered a lot of ground, from the structural steel of ResNet to the hardware-aware magic of FlashAttention, the alignment of RLHF, and the new frontier of world models like OmniWorld. We've moved from the history of the field to the logistics of keeping up in this crazy 2026 landscape.
It is a lot, but it is an exciting time. I think we are moving out of the brute force era of AI, where we just threw more data and more compute at the problem, and into a more refined era. We are seeing more clever architectures, better hardware utilization, and a deeper understanding of what is actually happening inside the neural cathedral, as we discussed back in episode 1097. We are becoming architects instead of just builders.
Yeah, that episode on decoding the hidden logic of these models is a great companion to this one. If you want to understand the why behind the how, definitely give that a listen. And if you're looking for the deeper history, episode 599 covers the decades of innovation that happened long before the world ever heard of ChatGPT. It helps to know that we've been solving these impossible problems for a long time.
It's all connected. The history isn't just a series of dates, it is a series of solved problems. Every paper we've talked about today was a solution to a specific wall that researchers hit. When you understand the wall, the paper makes so much more sense. It isn't just a document, it is a tool.
Well said. And hey, if you are finding these deep dives helpful as you navigate this crazy AI landscape, do us a favor and leave a review on your podcast app or on Spotify. It genuinely helps other curious people find the show. And we love hearing what you think. We might even use your feedback to shape the next episode.
It really does. We read those reviews and they help us decide which rabbit holes to go down next. It is our own version of human feedback.
You can find all our past episodes, all 1091 of them now, at our website, myweirdprompts.com. There is a search bar there, so if you are interested in a specific paper, or a specific topic like the KV cache, or agentic delegation, you can find the exact episode where we broke it down. We try to keep the show notes updated with links to the actual papers we discuss.
Thanks to Daniel for sending in this one. It was a good excuse to clean up my own reading list and think about my own hygiene. I think I have about 50 tabs I can finally close now.
Always a good thing. Closing tabs is the ultimate form of digital therapy. Alright, I think that's it for today. I'm Corn Poppleberry.
And I'm Herman Poppleberry.
Thanks for listening to My Weird Prompts. We will see you in the next one.
Keep reading, but keep filtering. See ya.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts.